everybody. So I have Desmos open, which probably isn't the most appealing site for a lot of you, but this is going to be an interesting one. And I'm going to first apologize for the lack of uploads in the past month. It's been very busy, but I think what I have in store for you today will save that. So today we are doing an introduction to raycasting. This is a companion piece to the asset I'm selling on my Patreon that's coming out, which is this mostly real-time planet, which is entirely done with raycasting. And it's an entire custom render engine. I'm going to close off some of this stuff because it's slowing me down. Actually, just screen recording in general is slowing this down a lot. It generally renders a ton faster. Anyways, there will be a documentation video for this coming within the next few days. It'll be up on my Patreon today or tomorrow. So yeah, I expect a featured and documentation video. This will be available for the $10 patrons. I think that's kind of a steal because, I mean, it's fully volumetric and there's volume shadows and stuff, so but I'll let you guys be the deciders of that. So let's get on with it. So we are going to start in Desmos. Here we go. So we're going to start in Desmos, and since this is an introduction to raycasting, the mathematical functions of raycasting are relevant, and understanding how it works is good because I don't want anybody copying my node systems node for node except for in rare cases, because I want people to understand what exactly we are doing. So I'm starting in Desmos for this exact reason. I'm going to explain the fundamentals of raycasting, and from there we can get on with it. So there's a bunch of functions here that you don't need to pay attention to. Let's just make it a little bit more interactive. So the first thing we need to know about raycasting is a method of shooting ray. Oh, it's a rendering method, right? This is what ray tracing is built on, ray marching. The fundamental principle is you have a point from which you are viewing the world, and you are seeing what is collected by certain rays that you shoot out of the camera. Now this function represents one ray. In reality, there's one per pixel. But we're going to use a singular case to illustrate our point. So each ray starts from the position of the I think we might want never mind. So each ray starts from the position of the camera, and each ray goes in the direction of view. Well, yeah, so if your camera is pointing this way, you're at the center of the screen, the rays will be also pointing this way, but other rays off to the side may shoot out up here or down there. I believe you can see my mouse. But there's generally a gradient of different, or there's a range of different rays in 2 dimensions that you can see. So raycasting. So we're going to be making a simple atmosphere shader, nothing as complex as what we did in, or what I did in the in here. This is far more nodes than I would ever expect to cram into a tutorial series. And there's more. It's a lot. And we're not going to be doing this. We're going to be doing something very simple, but it'll teach you a whole lot, and it'll introduce you to this method of rendering. And we're going to be doing it in the world shader nodes, so there's going to be some cool tricks, and it's not going to be in the traditional shader nodes. So fundamental to raycasting, and the reason why we have these two flat lines here is these are where our entrance and exit points are for the atmosphere. So we don't want to be casting rays out into infinity because that's simply impractical. We can choose an arbitrary value where if we cut the rays off at a certain point, we can preserve the look of the atmosphere, but we can also, but we also don't have to compute unnecessary steps. And we do the same with the bottom. So you can see you can move these around, all that fun stuff. So what we need to do is we need to find the position of the camera, we need to find the direction of the ray, and we need to find where this ray intersects with either the bottom or the top plane. Now there's actually a relatively simple way to do this. And for now, we're just going to be considering the vertical components of this, not the horizontal one. So we can literally just disregard whatever. We can take this out of the equation and just assume, well, actually that looks a little bit weird. Let's just, there we go. So we can just assume that since an atmosphere is uniform across, it's relatively uniform, especially if it doesn't have clouds, across the x values, we don't need to really pay attention to that. We only need to pay attention to how high up we are. And we're going to be doing a flat atmosphere, by the way, no ray sphere intersection functions. So the intersection for this is really simple, and we can sort of conceptually understand it before even write out an equation for it. So the reason we do this is, or the reason we can do this is because this is basically a function of simple transformations. So what happens if we move down? Now I'm going to move down. We can see that we're just scaling this intersection point right here. We're scaling that towards the x value of our position. And we can see if we go all the way down there, it intersects right there. Now what happens if we move side to side? We're just shifting it over, right? So let's write a function to find it for us. So we're simply solving an algebraic equation here. Alright, so I'm just going to copy this, and we're going to put in our bottom value, which is b. And we want this to be, let's see, yeah. So we have our bottom value b, and we need to solve for x, right? Don't get confused with this notation. This is direction of y, not dy. It's not derivatives, don't worry about that. So b, which is our bottom, equals this equation. So this equation equals b. So let's solve for x. So we first start by subtracting out ay from both sides. Multiplying by dx. Why do I keep doing that? There we go. And then dividing by dy. And then we can get rid of these parentheses and then add ax back in. Now since it's not responding very well to b, let's just plug in 0. And let's plot this. There we go, there's our x value. Pretty neat, huh? And we can see that is precisely where we do that. Now let's duplicate this for our top. I wonder if we can do this for b. Oh, looks like we can. Okay, so let's duplicate this and we can just plug in T, I think, and I think it's going to be nice. Okay, so now we can see fun. Now the node application of this is actually surprisingly simple. You're going to be surprised when you see this. So let's open up Blender and let's implement this. So, delete default cube, and then we're going to go into shading, world, go into rendered view, and let's implement this function. So we have dx over dy, right? That's going to be, so, alright, so let's first evaluate this. So, actually, let's look at the bottom first, so it'll be easier. So we have b minus ay, so it's the bottom minus the y. So ay, I'm sorry, I probably forgot to mention this. Ay is basically the y value of our position. Ax, x value. So what we need to do is we need to transcribe this to 3 dimensions. Now this is pretty simple because we just repeat this process, except instead of ay is az, and we do one for ax and then one for ay. So, but let's do this. So let's just assume our bottom is going to be 0. Okay. Our bottom of the atmosphere is going to be y equals to, or z equals to 0, and we are going to be floating somewhere in this. So that simplifies the first term to be just negative ay. And we actually don't really need to bother with these negatives a whole lot. So, by the way, I want to show you how to grab the camera position in the world shader nodes. And there's this node in the vector thing called the vector transform. So if you set this vector to be 0, set it to be point, set the world, the top one to be world, and the bottom one to be camera, or top one to be camera, bottom one to be world, you can grab the position of the camera, and I'm just rotating around here. So this is a fast and easy way to grab the position of the camera. So we are going to separate X, Y, Z. Now the implementation I said is surprisingly simple. So this is going to be nice. So we're going to separate X, Y, Z on this object output of the texture coordinate. Now, well, actually generated, my bad. So the nice thing about this is our view direction, guys. This is literally just a perfect map of which direction the rays are going in, because it's all direction based. Right? It's already normalized. All that stuff. So we can use this directly as, like, we got dx, dy, and dz here. dz is blue, dx is, I mean, we split out in here. So what we need to do is we need to combine x, y, z and just do these top two, and then converter, vector math, and we can just divide this by z, and we get this. It doesn't look especially great, but we get it. So let's we're gonna also want to multiply by our z because that's in our equation, right? And conceptually that makes sense, right? Because we're going down, or it's getting closer to us. Now I want to show you that this does work, so I'm going to do a checker texture. Oh, and don't forget, we need to add in our X and Y back. So converter, combine XYZ. These are going to go back into there, and we're going to add this. So I'm going to add in a checker texture. Plug that into the vector. Oh, sorry, you want to subtract maybe. There. Look at that. It's beautiful. Now this is showing our the top looks a little weird, and how we can do with that is we can add in a converter math node in between here and instead use absolute value. Actually, wait, no, that's going to just be a little weird. Oh, and set this back to add. My bad. So we can see now it's kind of looking okay, but it's also being weird, right? Because we can see that, like, it gets thinner. So what we need to do is we need to isolate the part that's on top and the part that's on bottom. We need to separate those from each other. And how we can do that is we can just use this Z value, and we can just say whenever this is greater than 0, do this. Whenever it's less than 0, do that. So this is where this comes in handy. So we're going to do a color mix RGB and plug the greater than 0 into the factor. And then we're going to duplicate these last two nodes because these are the only thing that's going to change, and the only thing that's going to change is this. So what we need to do here is, instead of using the same Z value from, like in our equation, we can clearly see that this term is different than this term because B and T are different. So we are going to be using a math node. So we're going to be using a math node. And we're going to be using subtract. And then this is going to be our top value subtracted by our Z. And now we can see it's behaving normally. I don't like how Eevee renders stuff in here. It's very weird and trippy. But we can see now it's working properly, and it looks like we actually have some sort of roof and stuff. Next thing we want to do is we want to clamp the Z value between our min and max values. By the way, this is going to make a top part, but if we want it to extend further, we can literally just add another add node, and this second value is going to be our bottom. So I'm going to add in an input value node, 2 of them actually. So I'm going to subtract. This is going to be our bottom height, and then this is going to be our top height. So top height, I'm going to set this to like 10. Bottom height, I want this to be at around like 0. And then what we want to do is we want to take this Z output and we're going to want to use a clamp where the min is the bottom height and the max is the top height, and just substitute both values that we're using it for that, and that'll work. This checker texture is annoying me, so I'm just going to use a noise texture. Because we can. It's pretty cool, eh? I like how this works. Now, all we need to do is fill it in with an atmosphere, but you're done with the first part, so congrats. We're going to end this tutorial by showing you how to get a simple volume computation. So volume emission is quite simple to do, and especially if it's uniform. And by the way, what we're going to be doing is volume scattering, so it's not just volume emission. But so we're going to add in a converter vector math, and then we're going to take the length. And for this, actually I forgot. So we don't want to have these on there. So we're going to take, we are going to take this lateral movement, we're going to take that off. And we want, so we're also going to add in we want to make this readable a bit more, so we're going to multiply by like a 101. And boom. So oh, I forgot one thing. So what we want to do here is we want to get the relative intersection functions. So we don't want to get rid of this, so I'm going to unmute this. But we need to take instead of the length, we need to get the distance from this, which is the actual position, and our camera position. So I'm going to duplicate that because we can do that. Get the distance there. Now one thing that we need to do here is we need to get the proper z values for us. So what I'm going to do is I'm going to add in a combine XYZ to each of these. Where the z value will be our bottom, or first one will be our bottom, the second one will be our top. So we need a group, bottom height, we need to plug that into z. This will be bottom. Oh, I forgot, so we need to put this clamp back. So we're going to duplicate this. We're going to put this clamp into this, and this is going to be the distance that we're getting it from. So we see an issue where it's still black over here, and that's what we're trying to fix with this, by the way. So we're going to duplicate this for the other one, and instead of bottom height, we're going to be adding the top height in this one. And there we go. You can see it's working properly. You can move up, move down, move it all around, all that jazz. So this is a fully fledged atmosphere system. One thing you might want to do is you might want to just renormalize this. So I'm going to multiply this by, I'm going to duplicate these, and then I'm going to subtract. Sorry, not multiply, we want to divide. Subtract bottom height from top height. And this is basically just going to make it so that no matter how thick your atmosphere is, it's still going to emit the same amount, which is quite nice. But yeah, look at that. Be proud of yourselves, folks. Next one might be a little bit harder, might be a little bit easier. It depends on how you approach it. But I hope this will be digestible for everybody. But that's about it for this tutorial. So I said earlier, I have a new Planet product coming out that's really cool. It's real-time and shit. It'll be on my Patreon today or tomorrow, so November 3rd or 4th. I'm still in the process of beta testing it, so I mean, you get what you get. I want to get this out or else it's never going to come out. But it should theoretically work and be able to run on your computer. In addition, I'm coming out with the feature video and just documentation for it today or tomorrow as well. That'll just be a companion to it. Same with this, because I want information to be free. I don't want to gatekeep information behind a paywall. So this is a simplified version of what I'm doing, which is basically raycasting and raymarching through an atmosphere. But if you want the product, you're going to have to pay for it. Because, well, I mean, I spent my heart, I put my heart and soul into it, man. Anyways, that's that. It will be available on the $10 Patreon tier, by the way. Now we also got a Discord server that's nearing 500 members, which is quite awesome. So if you, the link will be in the description. I've been promoting this quite a bit, and it's actually been growing, which is, again, awesome. So, have a good one, guys, and expect some more content pretty soon. I hope to actually complete this series, by the way. I've had a couple others where it's just one and done, and I never really came back to them. This, I hope, is not the case for this, so have a good one, guys. I'll see you later.